Now, question number 2 is about aliasing or aliasing, depends how you pronounce it. I say it aliasing, that's how I learned it before, aliasing. You see, I have this signal here, it is a continuous signal. I'm going to cut in few pieces, not necessarily 50,000, few points. I cut 0, this is my 0. And then I wait a little bit, and then I pick this point. I have another point. I wait a little bit, and then I pick this signal here, this one. And then I wait, I take another one here, and wait, take this one. And I continue. This one, this one, this one, and this one. Now, and I stop. So I do that for a few seconds and I stop. So just for this period, this is a continuous signal. Watch what happens to the output signal that is digitized, quantized, sample. All these sound almost the same. Now in continuous signal, between 0 and 1, there are millions, infinite numbers. In this continuous discrete signal, there is value, there is nothing. Value, nothing. Number, nothing. And so, if this is my computer, or pixels, so I have number, then I wait. Nothing, nothing. The time evolves, then I have here a value. Then I continue, time evolves, this is time. There is nothing, now I have a value. And then time evolves, I have nothing, then I have a value. Time continue, there is nothing, then I have a value. I continue, there is nothing, then I have value. I continue, there is nothing, there is a value. And then I continue, there is nothing, there is a value. I continue, there is nothing, and there is a value. I should have gone through the other side, probably outside instead inside, because the time evolved. So this way, like this. Okay, but you get the idea. You get the idea. See the difference between the original signal and the sampled one. It is completely distorted. It doesn't really look like this one. Almost you have the overlook, but it doesn't look like this one anymore. Now, if this is my voice, and you want to reproduce, it is digitized, and you want to reproduce, reconstruct, and recognize my voice, probably you will not be able, because you have lost a lot of information between this point and this point. A lot of things here are lost. So this is very, very low rate of sampling, very, very low. 1, 2, 3, 4, 5, 6, 7, 8 intervals. 8 intervals within a cycle. 8 intervals, that means 2 power 3. Power 3, that's the resolution is 3. Resolution is 3. So this is very, very bad sampling rate. And so what can I do to improve? To improve the sampling and have more information. Clearly, I have to sample more. That means I put this one, this one, this one, and so forth. Sample all these points. How many? Thousands and thousands. Probably I will end up with a decent number of samples, and therefore in the future, if I want to reconstruct my voice, I have enough information that you can recognize my voice. And so the bottom line is that higher is better. Higher rate of sampling is better for the future if you want to reconstruct your signal. And so now there is something we call Nyquist and Shannon theorem. If I have given a signal like this with the frequency and amplitude, what is the minimum rate of sampling that so that I can reconstruct this signal with the decent values, decent without that much information? Is it half, 3 times? How much? There is a theorem. You have to read on internet what is this Nyquist-Shannon theorem. It is a condition. And the distortion of the signal due to undersampling or oversampling is called aliasing. You may call it aliasing. So that's the subject of question number 2. So you are going to zoom in region of the peak and see what happens once you recognize the limits of aliasing first, the frequency. If you are given 50,000 sample, what is the distance frequency that corresponds to the limit of distortion? And then you put that frequency and show me a graph. So you will have here the limit. This is the limit. I want to see the graph. Then you have over limit or above limit, above, show me a graph, below, show me the graph. The distortion. Okay? That's where we're asking. That's it.